Hello everyone, my name is TREVONT Moore. I'm a student at Oral Roberts University and my project was on gradient-based discovery of initial feasible solutions for inverse materials design. This is my final presentation for the summer 2024 OREU program at Texas A&M. I'd like to thank my sponsors at the National Science Foundation, the Jet Propulsion Lab at the California Institute of Technology, the OREU program itself, and last but not least, my mentor, Courtney Kunzelman. My motivation for my project was that engineering businesses are wasting time and money by trying to find these feasible solutions in their high composition spaces. Starting from the background, machine learning allows people to find new materials or unknown information about known materials. Inverse materials design allows this to happen a lot quicker, but it's mostly do it yourself. Aspiring engineers want to create efficient tools for these businesses. My goal was to build a gradient-based optimizer, which means using a gradient-based derivative, I will be able to find solutions at functions when they're at zero. And they will discover regions of phase stability in high dimensional composition spaces, which means there are many phases to search through, but the optimizer is able to find what phases are which conditions that you are asking it to look for. And it does this by leveraging the differentiability of the residual driving force, which means you take the derivative of the residual driving force to enable you to find these solutions, and this will be shown later on. So starting from the very beginning of my introduction into the OREU program, I realized I needed to learn a few things before I could do anything. And those things were the basic terms of computational material science. I need to learn how to program in Python, which is one of the most common and popular program databases. I need to learn what PyCalFat is and why it's useful. PyCalFat is an open source Python library that is used for calculating phase diagrams. I needed to learn the problem as in the first step of the scientific process. I needed to learn the value of creating an adjustable optimizer, which is the gradient-based program that I will be designing that I will allow to adjust to the user's needs of whoever is using at the time. But I also came into the OREU program with the knowledge of general thermodynamic terms, math up to calculus 3. I knew how program generally works, and I knew how to use my resources to be successful. So going step by step from what I did, the first thing I did when I truly got into the program, and this was read/study my mentor's paper on using derivatives to find phase stability. This is definitely the field that she's working in and trying to get her doctorate, and she was able to coach me through. She helped me truly understand the information so I could reiterate it to ensure I understood what was happening. She helped me download GitHub and Anaconda and the necessary packages for it, which is packages that Python uses to whether to use PyCalFat or for other methods, but for me it was for PyCalFat. And then I had to run my mentor's programs used in her paper to ensure I installed everything correctly. So for minimization case number 1, I was given a set of parameters, a specific material, which is the nickel titanium alloy. I was given 2 specific phases of the material to look at, liquid and BCC-B2 phase, and I was also given some objectives to create a function that calculates the sum of residual driving forces, then use gradient descent to find the overall composition, which minimizes the sum of the residual driving forces. And on the right, it just shows how I put that in my code. So this graph shows what I'm looking for visually. We have the Gibbs energy on the y-axis. The x-axis is the composition for a certain component. The left mu sub A is the chemical potential of a component A. The right is a chemical potential of a component B. And the blue dot is showing where the vertex composition of a certain phase, whether it be alpha or beta, or this one on the left is alpha, meeting the target hyperplane, which is the horizontal line from one chemical potential to the other. And then the right is showing the vertex composition for phase B. And the green line is the residual driving force, which is what is measuring phase stability. So to find what I was looking for, I needed to write out the residual driving force equation based on my parameters, then create workspaces from it as well. I had to define the variables such as the Gibbs free energy, the chemical potential, the composition of titanium and nickel, and also define the residual driving force. I had to derive my function equations from the general residual driving force equation. I had to take the derivative of each equation for the gradient. Then I had to throw the results from that gradient into a gradient descent command to find the minimized overall composition of the system. So this graph shows each phase is listed on the right according to their temperature, to the composition of titanium, in this case, of that component. And so as you can see, not every phase exists at every point in temperature. So if I'm looking at a certain temperature, I can test for the phases that align in that spot. And so for minimization case number 1, I am looking at the BCC B2 phase and the liquid phase, and the temperature is 1550 Kelvin. So on the left, you can see that my code that I put to do the things I just described, defining and deriving the functions and variables, but I just wanted to highlight on the right that I derived the residual driving force equation for the B2 phase, and then for the liquid, they are two separate phases, but they are just denoted by the change of phase. This is my definition of the gradient function, which is where the meat and potato is once again, because I'm leveraging the differentiability of these functions to find my solutions. And that means I need to take the derivative to find what I'm looking for. So this is me taking the derivative of the function before. I just showed the B2 phase because also putting the liquid would take up a lot of room unnecessarily, when the only thing that changes is me denoting if it's the B2 phase or the liquid phase. So this one shows the result of my minimization case number 1. It says that under iteration 02, so it took the function 2 times to find the gradient descent by running it through the program. Using gradient descent to run through the program to find where the function was at a minimum, and that minimum was 0.455666517, which is exactly what I was looking for. And at the graph, you can also verify that that is where the graph appears to be at a minimum, which is correct. So after finishing minimization case number 1, my mentor gave me a new set of parameters for me to do a minimization case number 2. I use the same process from the last one as this because my objectives and material remain the same. Like I mentioned, a couple of parameters have changed, so I had to derive a new function to match it. This case wanted the equilibrium of 1 phase instead of 2, so this would prove that my program is adjustable. And once again, I'm using the nickel titanium system, which is simple, but it's great for testing a beginner program like mine. I put this graph back up just to note that I'm no longer looking for the B2 or liquid, but I'm looking for the BCC A2. And this the temperature given to me for this one was 1200 Kelvin. And if you track along, you can see that the BCC A2 phase is there at that time. This is showing just the code that I put just to note the residual driving force for this case and my derivation from it. This is showing the derivative of my derivation for the residual driving force, which once again, this is where the meat and potato is for me to be able to find the feasible solutions using gradient descent that I'm looking for. And this one was more unique because I hadn't come across one like it in my research due to the specific nature of it. The terms that are scratched out are canceled to equal 1, so you can just look past that. But once again, like I said, this one was unique, and also because I was looking for a single phases equilibrium, which is more likely what a scientist will be doing rather than looking for 2-phase equilibrium like in my first case. So this solution is what I was expecting as well. It says it took 1 iteration to find where the function was at a minimum, and you can look to the right and see clearly that when the y is at 0, the function is starting at about 0.8 going to 1, where 1 it is truly at 0, and that is where the solution was, which is exactly what I was expecting. So my gradient descent worked for this case as well. And in conclusion, and for my final results, I did build a working gradient-based optimizer. I or others could come and build upon my work to tackle real-world problems that are actually happening or people are wondering how to solve around us today. I was challenged to do something I've never done before. I did contribute to the world of computational material science, and although this project had no ceiling to it, I did go as far as I could with what I had. Thank you for watching.